In this video, I'm going to cover how to put uncertainty into spreadsheets and some of the statistical foundations that underlie uncertainty. So returning to our model of the car leasing business, I said there are two key uncertainties. There's the actual residual value of a car after 3 years that was leased, and which we don't know, and it's going to vary from car to car. And there's also this key uncertainty about the price sensitivity of customers, which there are ways to try to estimate that from data, but even if you have the data to estimate it from, it's going to be uncertain as to what the true value is. Nobody really knows how price sensitive the customers are. So those are two uncertainties I'd like to put in. Let's start with the residual value of the car. I've actually located some data here. This all comes from the Chicago area, and it's 80 cars that were BMW 3 Series cars, 3 years old, all with between 25 and 45,000 miles. So conceivably, this is the kind of car that would have been leased and might, at the end of 3 years, what it might be worth. And you can see there's a variety of values here. Now, one thing we could do, and actually I don't want to keep typing in the range here, so I'm going to want to put a formula. I want to find the minimum value in this range, and rather than constantly writing the range A2 to A80, it might be useful to define a name for this. Let's call it used cars. Actually, let's do it this way. No spaces, used cars. So we could find what the minimum and maximum were. Min. And all you do is have to put in used cars instead of the address. That's the minimum, 17,700, and the max used cars was 35,991. So we could say those are the sort of extremes. And maybe we want to put in the possibility that the used cars could be as cheap as 17,700 or as much as 35,991. So let's go back here to this model, and you'll find under the Data tab, What If Analysis is a Scenario Manager. Let's add a scenario here, which is the called the best case. And the cells we want to change for our scenario are these two: price sensitivity and the actual residual value. Click OK. It says, what do you want to put in for these? Well, the best case would be that consumers are not very sensitive to price. So as the price goes up, the monthly payment goes up, demand doesn't go down very much. Let's say instead of the 150, we put in 100 for that. And instead of the 24,210, we use the maximum, which was, I'll check it in a minute, but I put in 35. I don't remember the numbers, so I think I'm close, but we'll find out here in a minute. Missed it by $1, 35,991, and the other is 17,700. So I'll go back here. Go back to the Scenario Manager. Let's edit that one. 35,991. Let's add a new one we'll call the worst case. Changing those same cells. Consumers could be more price sensitive, let's say 200 rather than the 150 in our base case. And the car is really pretty run down when it's returned 17,700. Only about half the value of the best case. Now you can click the Summary tab. Oh, and the results cell, what we want to focus on is just the net present value. Click OK, you get a scenario summary. Here's our base case, 18,129,000. Best case is about 96 million. Worst case comes out at 84 million. Well, it doesn't seem like a worst case when our base case actually comes out lower. So that's one problem with this, is that they're not clearly best and worst case, because there must be some interaction between the value of the used car and the price sensitivity that makes our base case actually worse than what was done as the worst case. But there's a more fundamental problem regarding uncertainty here. This is not a very good guide, because we don't really know what's meant by best case. It happens to be, when you look at the value of the car, it happens to be the most valuable car among the 80 that I had data on, but tomorrow a car could be driven in that is more valuable than that, or less valuable than this one. It's a limited sample we have here, and there's no real saying it's absolutely the best or the worst. Further than that, I don't know the best and worst are particularly meaningful. To make business decisions on the basis of the very worst thing that could happen or the very best thing that happen is not very sound logic, because in fact, even this best, the most valuable car here, what if the next most valuable car was only 26,000? We'd have one car that was an outlier, and we'd be basing our decision on looking at a fairly extreme, unusual outcome. The problem with this kind of scenario development, which many companies use actually, they do treat uncertainty by looking at what they'll call either best case or optimistic cases and worst case or pessimistic cases, is that there's no assessment of how likely these things are. So is the best case something that happened 5% of the time, 10% of the time, 1% of the time? And if you ask subject matter experts to say, well, what do you think? Yeah, let's say you went to the marketers and said, what do you think the best case is in terms of how unsensitive consumers are to price changes? They might give you an answer, but do they think the probability is 5% that it could be that high, or that low price sensitivity, or they mean that's 10%? And they probably don't even know. If you ask them how likely is that value, they probably can't give you a reasonable answer to that. So we want to be able to do something much more systematic with uncertainty, and the scenarios don't do it. They display nicely. It's a very nice way of presenting results, but there's no way to assess whether the scenarios are reasonable, how reasonable they are, how likely they are. That's what we really are searching for, is more definitive information than that. So we want to represent uncertainty somehow using, we want to be able to talk about the how likely various outcomes are. It actually occurs to me one thing I should change, because it's possible that might account for why that worst case was not so bad. Over here, you remember when I drew the demand curve, I changed it to a maximum of 0 of the calculation to avoid negative numbers. But I don't think I did that over here. Yeah, that just shows that calculation, and when the price sensitivity is high, you could easily get a negative number there. So let's make this the maximum of 0 in that calculation. And I don't know if this automatically adjusts. I don't think it does, so let's just do this once more. Ah, that was the problem. Worst case comes out with no profit, because in fact, when it's that price sensitive and the actual residual value is this low, you would have to set the monthly payments so high that you would not have any leases. So basically, the worst case is the leasing business disappears. And that really reinforces why scenario analysis is not really a useful way to look at uncertainty. So you'd say basically, well, it could be anywhere from 0 to $96 million profit. Well, could be anywhere in there. Does that mean those extremes are equally likely, or how often will they happen? There's no assessment of that. So we'll go back to our used cars here. And what we want to do is we want to talk about how to sort of summarize this data that varies. The used car prices vary between almost $18,000 and $36,000. So there's a number of ways we could try to express this range of values. The first thing that you might do is you want to look at the mean value. Sort of what's the average of these, and we'll in fact do the average. So that's the $24,210 that was in the original model. But that doesn't capture the variability. It just tells you that sort of if you had to use a single number, that might be the best one to use. But in fact, if it's a skewed distribution, which we're not sure if it is or not, in other words, it's not symmetric on either side of 24,000, the median value, which is the value that half of the cars are worth more than that, half are worth less than that, might be a more useful measure. More typical of where the data is. For skewed distributions, the median, the 50% point of the data, is usually more meaningful than the mean. So instead of 24,210, that's 23,828 or so. Let's just go ahead and format those in dollars. So those are two alternative measures of sort of what, if you had to pick a single best number to use, pick one of those. But we don't want to pick a single best number. We want to reflect the actual variability in this. So we need to look at some measures of how variable they are. So one measure we could use is the range. And I don't think there's a range function, so we actually, it's the maximum minus the minimum, so we can already do it from the calculations we have, G2 minus G1. So there's an $18,000 plus range between the minimum and maximum value. Range is not a very useful measure for variability though, because it does show you the extremes, but if those extremes are highly unusual, and they're almost guaranteed the bigger the data set you have. If you have 1 million cars, there's going to be something out there that's a real outlier, far away from the rest of the data, and it will directly affect the range. So the range may not be the best measure to use. Another measure of variability would be to look at the percentiles. From the 25th percentile to the 75th percentile is what's called the interquartile range. I'm not sure if there's an Excel function for that, but we can, no, there's not. So what we have to look at is percentile is the kth percentile, k between 0 and 1 in a range. So we're going to do, the array is used cars. And we'd want it to be between 0 and 1, so we want to look at the 0.75, 75th percentile, minus percentile /25th percentile is $5,602 between the 25th and 50th, 75th percentile. Half of the cars are within a range of 5602. That is a somewhat better measure of how variable these are. Yet another measure that's common to see is the standard deviation. Standard deviation is, many people kind of just blank out when they hear the word because they don't really know what it means. And the calculation, the formula makes it not easy to understand, because what you actually do is you look at each of these values, see how far it is from the mean. So you subtract the mean from each of these values, you square that amount, you add that up for all of the values, then you take the square root and you divide it by the number of data points you have. Not at all intuitive, except that it is kind of, not exactly, mathematically it's not equivalent, but the best interpretation you can give for the standard deviation is it's a measure of, on average, how far away each car is from that mean. You won't get it, it's not that exact calculation, but it's approximately the same thing. So the standard deviation, which does have a formula, standard deviation of used cars, is a little less than $3,800. So the way you would interpret that is you'd say, roughly on average, the variability of these cars is that the average car is $3,800, either higher or lower than this mean of 24,000. So standard deviation is a measure that captures, in some sense, all of the cars, but talks about how far away the average car is from the mean. Now, one of the reasons for having that standard deviation is that one way to represent uncertainty is to assume that this mean and the standard deviation characterize the possible values that the car can take in. And we might do that with a normal distribution, famous bell-shaped curve. You're probably all familiar with having seen bell-shaped curves. They are used to describe lots of things that vary, people's heights, not people's incomes. Unfortunately, they don't look like a normal distribution. We've got a few Bill Gateses and Warren Buffetts, and the mass of us make a lot less than that. But many physical quantities actually follow fairly normal distributions. So that would be one way to describe this. Now, what I'm going to do is talk about some probability theory here. And probability theory can become extremely philosophical, and there are some major schools of thought, but I would sort of say there's three basic approaches to probability theory. One of them is a theoretical approach, and that's historically the one that's been used the longest, and that's based on games of chance. Card games, poker games, roulette wheels, dice, flipping coins. These things follow particular kinds of predictable patterns. The uncertainty, the variability is something that we can characterize and follow certain sort of natural laws, just like in physics, gravity and wave patterns follow physical laws. So there's the sort of theoretical way of deriving probability. Then there's a a frequency approach to probability that says that the probability of something happening can be characterized by how frequently it has happened in the past. So you have some data that actually says, here's how frequently something happens, and that's a good way potentially of measuring the probability it'll happen. And the third way is to use subjective probability, where you basically make your own judgment about the probability that things might happen, or you attach probabilities to how likely you think all possible outcomes are. And we'll look at examples of all three of these here momentarily. Let me start with the theoretical one, because it's probably most familiar to you. Let's say you have a pair of dice, and you're just going to roll the dice, and you want to see what kind of number comes up. So I've done a little spreadsheet here that shows the two dies, and the first die can come up with anywhere from 1 to 6, and then die 2 can have anywhere from 1 to 6. And so I have all the possible combinations here. There are 36 combinations that could occur if I roll dice once. Here's the sum of the two numbers that appear. And you can see that the outcome of rolling dice once varies. How can we characterize that variability? Well, there's a couple of ways to do it. One is it helps to have a picture of this. So I'm actually going to create a little table showing the possible outcomes. Well, 2 is the lowest and 12 is the highest. So it'll only be values from 2 to 12. If you go into the Data tab to Data Analysis, and if on your computer you don't see Data Analysis and Solver, they are there, they're installed with Excel, but they're not automatically activated. For some reason, Microsoft has done this ever since the very first version of Excel. They have a lot of statistical tools built into Excel that you don't see unless you know to look for them. So if you don't see them, what you should do is go to File, Options, to Add-ins. And if you look at Manage Excel Add-ins, you should click the one that says Analysis Toolpak or Analysis Toolpak VBA, either one of them, and the Solver add-in. You really might as well activate them. They're already on your computer. As soon as you do that, give it a second, these will appear in the Data tab. And if you click on Data Analysis, there's a whole bunch of statistical capabilities that Excel has that you can find under this. The one I want to use here is a histogram. When you click OK, it says, well, where is the input range? And I should be able to type use cars here. The bin range is what I just created. What do you want to show the bins for drawing this picture? And we'll paste this right into the sheet. And what I want, I'm actually going to click the cumulative percentage and the chart output. Oh, excuse me. It's not. Let's undo that. And I have to clear that out. I'm not up to the use cars yet. That's what went wrong here. So let's do that again. Histogram. We will do that in a minute, but not now. Correct dice. This is the data. Got ahead of myself there. The bin range is correct. That's a bit better. Make this bigger. So what we have here is the blue bars are what would be called a frequency distribution. It shows how often different numbers come up, and you can see that 7 is the most likely outcome because there are a lot more ways of getting 7 than there are of getting 2. There's only one way to get 2. You have to get a 1 on each die. But you can get a 7 by having a 2 and a 5, or a 1 and a 6, or a 4 and a 3. There's lots of different ways. So there's a higher frequency of 7 than any other number, followed by 6 and 8, 5 and 9, and so on. The cumulative frequency, it has the scale on the right and shows that when you get to 12, you reach 100% of the possibilities. And at 2, it starts off really quite low. The frequency is measured here in the number of times, number of ways that you can get that outcome. And the cumulative is a percent here. It might be helpful to have the frequency appear as what fraction of the time instead of what total, instead of how many times it happens. So when you see the frequency here, instead of putting the frequency, let's put the fraction. And so that frequency of 1 for getting a 2, let's recalculate that as I2 divided by the sum of I2 to I12. And actually we'll make it $I2, $2 to $I12. So in other words, I've got 36 possibilities here. I'm basically going to divide this 1 by 36. 1/36, or a little less than 3% of the time, is how often I get a 1. And the 7 occurs 1/7 of the time, 1/6 of the time, 16.66%. In other words, it happened 6 out of 36 times, and you see it's 6 up there. And we can actually just change our picture here. Take the frequency and edit that so that the values are, let's call it frequency with a small f, and instead of using the original data, change it to this fraction of time. And the reason I did that is that we can actually now interpret these blue bars as a probability. If I said, before I've rolled the dice, what is the probability I'll come up with a 7? A reasonable way to estimate that would be to say it's 16.67%, 1/6 of the time. There's a 1/6 probability I'll roll a 7, based on the theoretical properties of how often these things can happen. So didn't roll dice a bunch of times and look at the data. I basically just put down all of the possible things that can happen, because I know all the possible things that can happen when you roll 2 dice. And in fact, these are theoretically derived probabilities. The probability I will get an 11 is 8.33%. So that is a way of interpreting a probability. And on top of that, there's also a way that we can, there's a mean of this distribution. You can see what the mean is. The mean is 7. and that's the average value. It's also the median value, and you can measure a standard deviation of this, and there's a theoretical formula you can use to calculate the standard deviation. So we've just now taken a theoretical view of we've outlined all the things that could happen with two dyes and derived what the probability of each of those outcomes is. This is a probability distribution. And so the important concept here is one of a distribution. That is the fundamental object that we use to describe things that can vary. Distribution describes all the possible outcomes and how likely they are. Because it describes all the possible outcomes and how likely they are, a probability distribution should, if you look at the cumulative probability distribution, should reach 100% when you've covered all of the possibilities. It should never go over 100% because you can't have more than 100% of the possibilities. And it should reach 100%. If it doesn't reach 100%, you're not looking at a probability distribution because there's clearly something else that can happen that you haven't accounted for. So probability distributions basically have to satisfy that each of the outcomes has a probability no less than 0, no greater than 1, and that the sum of the probabilities across all the possible outcomes is equal to 1. If those two things are satisfied, you can be talking about a probability distribution. And we just derived one for dice. Let's see if we could derive one for our used car prices. Well, first let's see what it looks like. Let's look at a histogram of these. Now I think I can use the used cars. Oh, I need a bin range first. We'll have better tools with other software. The histogram is kind of clunky in Excel because you have to develop a bid range first. Well, we sort of know what range we want because we can see the prices go from 17,000. Let's do them in let's do 17,500, and we want to go up to 36,000. So those will be my bin ranges. Now I can go to data analysis. Used cars. The bin range is there. Let's put it over there. I'll ask for the same things. Now you see the blue bars, my histogram. Doesn't quite look as neat as it did for the dice. You can see that it's not a symmetric distribution. It seems to be a little skewed. This is what's known as a positive skew. Most of the values are actually below the average. We know what the average is. The average is 24,210. So the average is sort of right around here. And there's more values lower than that than higher than that. The median is at 23,800, something a little less than 24,000. So somewhere in here is where half of the data is higher and half is lower. The cumulative distribution does go up to 100%. So I think we could interpret this as a probability distribution. All of these, well, the problem is we have frequencies here. So let's actually come up with the little f frequency, just like I did before. We'll take N2 divided by the sum of $1 and $2 to It's $41 and $41. And for my graph, let me edit the frequency, name that, values, replace the actual number of times it happened with what fraction of the time each of these values or ranges occurred. Since all of these values are, none of them are less than 0 and none are greater than 1, and since they add up to 100%, I could interpret this as a probability distribution. And this is that second way of conceiving a probability as a relative frequency. My interpretation here would be how often is a car, a used 3-year-old used BMW, is the actual, how often is the actual residual value between, I think it's 23,750 and 24,250, and the answer is a little over 11% of the time. So I could interpret that as what is the probability that my actual residual value will be in that range? A little over 11%. What is the probability it will be as high as 36,000? A little over 1%. I'm basing my probability on actual data on the relative frequency with which it occurred. That is extremely useful if you have a lot of good data to base it on. The risk is that the next car that rolls in might be somewhere completely outside of this range. Since you didn't have any data that was outside of this range, you're basically assuming that's not possible. When if your data is not very extensive, of course it's possible to be outside that range. If the data is pretty robust, you have a lot of data, then I think it's reasonable to interpret the relative frequency with which something happens as a probability that it happens. So what I could do now is I could go to my model, and instead of doing the actual residual value at 24,210, I could say, and this is software that we will be using in the course, I could say let's put a probability distribution on that. Let's use a normal distribution. Where the mean let me actually do it this way. The mean, and we've got it over here. The standard deviation, I calculated there, and a normal distribution, which is a bell-shaped curve, it only has 2 parameters. It has a mean value and a standard deviation value. That's what the distribution looks like. 24,210 is the mean. The normal distribution is bell-shaped, so you can see that with this standard deviation, it ranges from about 14,000 to 34,000. So I could use that to describe the probability associated with these used cars. Now, notice I've made an assumption that is not quite realistic, at least compared to the data I have. According to this, there's almost no chance it will be above 34,000. And I have one used car that's almost worth 36,000. According to this, there's some sizable probability that it will be worth less than 18,000. In fact, about 5% of the time, it could be worth less than 18,000 when I only had, I think, one car that was worth less than 18,000 in my data. So by approximating my used car data with this distribution, you could say that I've now introduced an inaccuracy because, in fact, I have things that don't happen in my data set that could happen. Or you could say it's an advantage because I only have data on 80 cars here. And like I said, the next car could be outside of that range. Well, this does allow the next car to be outside of the range of what we've observed. So it might be an advantage to replace the actual data with a distribution that approximates it. So for now, just bear with me because we can do better, but for now I'm going to use that one. And I'm going to let me see where I don't want the graph, I just want to insert the distribution. Oh, I've got it in that cell. And you'll notice that the formula, it's an Excel formula, at risk, which is this add-in, all at-risk functions start with the word risk. Risk normal says put a normal distribution in here where the mean is given by that first cell address, which is on the used car tab. The standard deviation is given by the cell G8 on that tab. And risk static is just basically saying what value to put in this cell while you're not, just as a placeholder, what shows up in the spreadsheet. And actually, I don't think I want the standard deviation to be what shows up there. So let's put our 24,210 back in as our placeholder. Oops. Oh, so the static value right now will show is 24,210. But what I really have in this cell is that bell-shaped curve that we just looked at. So let me quickly go to the third type of probability, which is a subjective probability. I don't really have any data here to try to estimate the price sensitivity from. And what I did when the scenario was I said it could range from 100 to 200. Let's use, for a subjective judgment here, a different distribution. A common one to use is what's known as a PERT distribution. And let's say that the minimum, it could range from 100 to 200, but the most likely value is 150. And the static value that I'll put in that cell is the 150 we had before. Here's what that distribution looks like. It looks a lot like a bell-shaped curve, but it actually is different in an important way. It's kind of squeezed in more. The PERT distribution is commonly used for making subjective judgments about probability because it's not very sensitive to the minimum and the maximum. If you change this minimum to be 50, it's pulled out on the left side to 50, but the middle is still pretty close to 150, and the bulk of the distribution has stayed in the same place. If you even change that minimum to be 10, it hasn't changed shape very much. And the value of that is that often for subjective judgments, you approach subject matter experts, like somebody in marketing here, to try to tell you how much they think demand is influenced by price. And it's hard to get a reliable estimate of minimum and maximum. How low can the value be? How high? For the same reason that the scenario analysis doesn't work very well when you try to say what is the worst case and the best case. They're probably better able to tell you what they think the most likely value is. So the PERT distribution is not very sensitive to the minimum and maximum values. The most likely value is far more important, but it does allow the value to vary. And so I'm going to use this one. Notice what the formula looks like. Risk, because it's one of the at-risk functions. It's a PERT distribution. It has three parameters. What is the minimum, the most likely, the maximum, and the static value that I want to appear in this cell right now is 150. So I've got two different kinds of uncertainty I put into here. I put in a uncertainty based on a probability distribution based on a relative frequency that something happened, looking at the actual data. And I had a subjective judgment about how likely different price sensitivity values are, anywhere between 100 and 200, with 150 being the most likely. And what at risk does is it allows you to do what's called Monte Carlo simulation, which says, let's go and into these distributions, those pictures that we just looked at, and let's go in and grab a random selection from that distribution. In fact, there's a little button here that will randomize this. The computer just went in and picked out price sensitivity of just about 150. Oh, not much different at all than what it was, and an actual residual value of 23,163. If I press F9 again, goes in, picks out another random draw. Price sensitivity a little less than 149, 23,768. As you hit F9, it's constantly picking different random draws from that distribution. And what you really want to do is a lot of time. So you don't want to be pressing that. What you want to do is say, let's run a lot of these random draws. We'll do 5,000 of them. And before I start it, what I want to focus on here as an output is my total net present value. And I'll start the simulation. It ran 5,000. What are we looking at? We're looking at a histogram of the outcomes. In fact, if you look on the right, you'll see that the mean value is a little less than $9 million for the net present value of profit. The median value is $2.5 million. It's a skewed distribution. You can see the right-hand skew here. Most of the values are, the median value, 50% point, is quite a bit lower than the mean value. The mean is being pulled up by those high values. You can also see different percentiles of that distribution, different placeholders. In fact, it looks like almost half of the time I actually get, well, I shouldn't look at that way. 20% of the time I actually am losing money. And then from 20 to 50%, another 30% of the time I'm making zero, which probably means I'm not having any leasing business. There's no leases at all. And then half the time I make money. With the average amount that I'm making actually not bad, over 9 million, or just about $9 million. I think we can actually put a cumulative distribution here. And so you can see how the total probability rises as the value goes up. When you get up to 100 million, you've got basically 100% of the probability. At 0, notice the jump from 20% up to the 50%, all have the value of 0. This is the chance of being below 0 is about 20%. That's the cumulative probability. I'll go back to the histogram. One other thing you can do is when you have this histogram, actually at risk will try to fit a distribution to that. The red doesn't look like it fits very well, but in fact, fitting a distribution is not a bad idea. So let's return for a moment to this, and let's look at the used car prices here. Why should I assume it's a normal distribution? Let's see what the distribution might actually look like. My at-risk has an option here for distribution fitting. Let's fit to used cars. Notice it highlighted my used car series because I gave that range name. Click Fit. And let's make this big so we can see what it's doing. So it has different criteria for fitting distributions to the data based on basically how close the actual data, the blue bars, are to the curve. And even though it's a mathematical calculation that ranks these distributions, you should always look at it visually to see if you like the description. So this extreme value distribution was the best fitting one mathematically. And it doesn't look bad to me. It looks like the general shape, you know, it's a somewhat skewed distribution. If you flew the red, you can see that if I use the red instead of these actual values, I'm going to get occasionally cars that are worth as little as $16,000 after 3 years' time, even though I have nothing really below just under 18,000. So I'm going to get some lower values. I am going to get also some higher values, but the vast majority of the time I'm going to be in that same range. We could compare that to the Weibull distribution, which is the green. Perhaps the green is a better description, even though it doesn't fit quite as well. You'll notice that the green gets cut off here, so you're not going to get really low value cars. You know, it doesn't happen often, but it won't happen really at all compared to the red. And a little less often will you get the higher value cars. So it seems to describe the middle a little better. Notice down here, the normal is pretty far down the list. If you want to see what the normal distribution looks like, and actually let's take off the top one, the extreme. The normal distribution is the green. And the green is not really a very good distribution. It has far too high a probability of getting a really junky car back after 3 years, and too low a probability of getting a good quality car back. And it's symmetric when in fact the blue bars are not symmetric. So I wouldn't want to use that. I think the normal distribution is actually not a bad, I mean the Weibull is not a bad description of the outcome. Let's write that to a cell. And it wants to know, where do I want to put that? Let's go into the model and put it in there. Notice what's happened here. It's now changed to a risk Weibull. There are parameters. If you look up the mathematical form of a Weibull distribution, it has kind of a messy formula, and parameter, it has 2 parameters, and the 2 parameters don't have an easy interpretation, but those numbers were estimated by that best fitting distribution. It's put those in. It's shifted the distribution a little to make it fit better, and basically, instead of the normal distribution, we now will use that Weibull distribution, and I can rerun that simulation. And that's only the, so what's showing is the input here. So the I put in the blue as the Weibull distribution, and 5,000 simulations filled that out nicely. So the computer's doing a good job of picking random draws out of that Weibull distribution. It approximated it very well. What we really want to look at here is the output, though. Browse results. And what we want is, oh, that's okay. There. So this is with the Weibull distribution, which is, I think, a better description of what we know about the used car prices from the data we have. You can see instead the mean value is a little bit lower than it was before. Instead of being almost 9 million, it's just under 8.5 million. The median value is quite a bit lower. It's only 600,000. If you look at the centiles here, again, 20% of the time we lose money, and another 25% of the time we have no business. But the other 55% we make varying amounts of money, and you can see how much. So there's a big spike here at 0 because there are a lot of circumstances in that simulation we ran where we ended up with 0 leases and 0 profits. But what we're able to do is put in 2 types of uncertainty represented by probability distributions. One of them being a subjective judgment, which I used a particular distribution called the PERT distribution for that, and one for the actual residual value, which I based on data by fitting distributions to the data. And the distributions, there's quite a wide variety of distributions that at-risk has to try to fit, and it looked like a reasonable description of that data. So using that fitted distribution, we can simulate the things that can happen, and we actually have as an output a probabilistic description of how much money we'd make. Now, of course, we still left with the fact that I used the same interest rate and contract residual value that I did originally. And what you really want to know now is, with this uncertainty, should I change those? And we'll see that at-risk can do that for us as well by now re-optimizing what is the best interest rate and residual value given the uncertainty that's in there. But that's for us to do in person. So what I tried to cover here is just basic probability concepts, where they come from, how you can represent probability in a spreadsheet, and a little bit of a preview of how at-risk puts that uncertainty into a spreadsheet and allows you to run a simulation so that you actually have probabilistic assessments of how likely different outcomes are from the model that you've built. There is an assignment that you should do, a pre-assignment, and the instructions are on CECnet. You'll see that you have to build a spreadsheet model for a very simple project. In class, we'll be using Microsoft Project along with at-risk, but I want you to do this just using an Excel spreadsheet to build a spreadsheet model. You don't have to, you don't do any simulation. What I want you to do is just use scenario analysis to explore some sensitivity to uncertainties. So don't forget to look at that and do that.